So let's talk next about knowledge graph completion task and various methods to accomplish knowledge graph completion. In particular, we'll talk about methods that are that right now will have cryptic names, but it will become clear: TransZ, TransR, distmul, and complex. So I'll introduce what these methods are, and we'll be in particular interested what kind of relationships can these methods capture and predict. So let's think about knowledge graph completion task, where basically we are given an enormous knowledge graph, and the question is, can we impute, can we predict missing information because the knowledge graph is incomplete? And the way the knowledge graph completion task works is that we are given the head node, we are given the relation type, and we'd like to predict the missing tail. So notice that this is slightly different from classical link prediction task, where nothing is given, we just say predict what links are missing in the entire graph. Here we would actually say, we are interested in this particular node, we are interested in this particular relation type, and we want to ask, where is this particular author, which other, let's say, genres is this author connected to? So for example, J.K. Rowling, right, the Harry Potter author, is connected to, let's say, genre science fiction. So that would basically be something we would want to predict. So what we are given is the head node, we are given the relation type, and we want to predict the tail. The way we are going to do this is we are going to do through node embeddings, right? So every node, every entity in the knowledge graph will have an embedding. And we are going just to use shallow embeddings. So basically it means we will want to learn an embedding vector for every entity type in the knowledge graph, so that we can then do prediction well. So the point is, we won't be using GNNs. We'll just assume we are doing shallow encodings, but you could also use GNNs if you would like. So knowledge graph representation will be such that knowledge graph is represented as a set of triples: head, relation, tail, right? So head is the source, relation is the type of a relation, and tail is the endpoint of the relation. So head could be Barack Obama, and relation would be nationality, and the tail would be United States. So the key idea how we want to do this is that we want to model entities and relations as embedding points and vectors in the embedding space. And we want to associate entities and relations with shallow embeddings, as I mentioned. So we are not using GNNs just for simplicity to keep our life simple. And then the idea is that given a true triple head, relation, tail, the goal is that the embedding of head, relation should be close to the embedding of the tail. So I know this is a bit abstract right now, so let me give you explanations. How can we embed head, relation, and how do we define this closeness that the embedding of head, relation should be close to the tail. And really all different methods we'll talk about differ how this closeness and how this embedding is produced. The simplest idea and kind of the most natural one is called TransZ, and TransZ basically has this intuition of translation, where basically the idea is that for a triple head, relation, tail, we want to learn the embedding of the head, we want to learn the embedding of the tail, and we want to learn also the embedding vector R. And the idea would be that we want to find these embeddings in such a way that head plus the plus vector R gives me the point where the T is embedded. Right? So, for example, if Barack Obama nationality United States, then I want them to be embedded in such a way that if I start with the head, I start with Barack Obama, I move according to this relation vector R, I would end at the point where United States is embedded. And of course, I don't want this to only work for, let's say, Barack Obama. I'd like this to work to be true for any person and their country of birth, right? So for example, if in this graph, I don't know, it would be myself here as well, maybe I'm a point here, then if I would move according to this vector R here, I'm from Slovenia, so my nationality should be Slovenian, so the country of Slovenia should be mapped somewhere here, right? Basically, I would apply the same translation, and hopefully the country that is embedded close to that point is the country of my nationality, right? So here's the idea. So the scoring function that would measure proximity between the head and tail would simply be head plus this vector r minus the tail, right? It basically says what is the distance between h plus r and the point t. And here I could use, let's say, Euclidean distance if I would like. So this is what is trans Z. Basically wants to learn these translations in the embedding space so that you can get from head according to a translation that is relation specific to the tail of that relation. I won't go into details basically of the learning algorithm, but essentially the idea is that you wanna have entities and relations that are first initialized uniformly, right? You want an embedding for an entity, you want to learn the translation vector for a relation, these are all the parameters of your model. You would, sample a positive example, a positive triplet. You would, for example, sample what is called a corrupted triplet, where you would have the head, the relation the same, but you would pick kind of a random tail. You would pick a country that is not the true country of nationality, and then you would say, let me try to find the embeddings, the values for head, relation, and tail, such that the distance between the real tail and the corrupted tail, the real tail and the embedding of h plus r is smaller than the distance between the h plus r and the corrupted tail, which basically means a country that is not the true nationality. And you can basically do the learning. So now that we have done this sounds like a great, very natural idea. What is cool about it is that now we don't only think of the embeddings as points in the space, but we also learn this vector r that allows us to move or translate between different points. It allows us to move in a given direction. And of course the question is, what kind of relationships is this type of approach able to learn? And when I say what kind of relationships, I really mean relationships with different properties. For example, some properties might be symmetric or reciprocal, right? If person 1 is a roommate of person 2, then person 2 is also a roommate of person 1, right? It's mutual. For example, then there might be relations that are called inverse, right? If I am someone's advisor, then that other person is my advisee, right? So advisor and advisee are kind of inverse relations. Whoever is in relation of advisor in one way, advisee is in the other direction. So the question then becomes, can we categorize this type of relation patterns or relation properties? And are these knowledge graph embedding methods like the TransZ that I discussed, are they expressive enough to model these patterns? So the relation patterns we are going to discuss are four. First is symmetric and anti-symmetric relations, right? Like a family, roommate are what we call symmetric because they are reciprocal, right? If I'm your roommate, you are also my roommate. It cannot be only one way. Anti-symmetric would be part of, hyponym. So it's basically one is with relation with the other, but not the other way. Inverse relations would be like advisor-advisee, where if I'm related to you with one relation, you're automatically related to me with a different relation. Then it would be transitive relations, for example, friend of, which would be if x is friend with y and y is friend with z, then x and z are also friends, right? So this would be one way of having the notion of transitive relations. Or if you think about relationship type, those are also transitive. That, for example, I say my mother's husband is my father. So that's also saying, if you start with me and you transform according to the mother relation, and then you take the mother point and transform according to the husband relation, you should arrive to the same place if you take myself and transform me according to the father relation, right? The two embeddings should meet. And then another important thing is that there are one-to-n relations. For example, student of, right? I can have multiple students, or I can have multiple advisees, so I can have one-to-n relations. So these are different relation patterns we are going to consider. And what we are going to do next is we are going to look whether TransZ is able to capture this type of relations. So for example, let's first talk about anti-symmetric relations. What would this mean is H is related with T. T cannot be related with H according to the same relation, like part of hypernym is an example. And TransZ captures this, right? Because if I go from head according to the relation vector R, I arrive to the tail. But now if I'm at the tail and again apply this relation transformation R, I don't get back to H, I get to some other point. So this means that TransZ naturally captures this anti-symmetry of relations that have this property. Another question is, can TransZ capture inverse relations like advisor-advisee, right? So if H and T are related by R2, then there is some other R1 that makes tail and the head related, right? Can we model inverse relations? Yes, we can. Simply the R2, the vector R2 should simply be the negative of the vector R1. So it means that from head, according to R1, I move to tail. Then if I want to move from tail back to head, I just move in the opposite direction. So in TransZ, this is naturally captured, naturally doable, so inverse relationships are possible. How about composite or transitive relations, right? Where I say if X and Y are related and Y and Z are related, then X and Z should be related as well, right? So in TransZ, you can simply do this by saying R3 is simply a summation of R1 and R2, right? So if I go from X via R1 to Y, and then I go from Y via R2 to Z, then I can basically simply go from X to Z according to R3. And R3 is simply the vector R1 plus vector R2. So again, we can do composite relationships with TransZ easily. So how about some relationships types that TransZ cannot capture? So for example, interestingly, TransZ cannot capture symmetric relationships, right? Relationships where like family or roommate that are reciprocated, right? Basically saying if H is related with R to T, then T should be related to H with R as well. And the point is this, right? If you go from H according to R to T, then what you'd like to do is apply the same R to T as well and get back to H. And the only way you are able to do this is to make R to be 0, which basically means that H and T are embedded on top of each other. But that is not good because H and T are different entities. They are distinct entities with distinct properties. So this means that TransZ cannot embed and cannot do this kind of symmetric reasoning, or it cannot model symmetric relations. And then another part that TransZ cannot do is one-to-n relations, right? The idea is that if I have a head and a relation, and maybe this is a one-to-n relation, then basically I wanna go from head according to relation R to T1, and I also want to be able to go from head according to relation 1 to T2, right? Both exists in the knowledge graph. For example, student of, right? I can be a mentor or I can have two students simultaneously. And again, TransZ cannot model this type of relations because again, the only way for this to work would be that T1 and T2 map into the same vector. They map into the same point in the embedding space, so that when you go from H according to R, you arrive to the same point. But again, this is not good because this would mean that T1 and T2 are the entities embedded in the same point, so they are indistinguishable from one another. But in reality, T1 and T2 are completely different entities. So this is what trans Z cannot model. So let's look at a different method called trans R that will allow us to fix some of these issues. Right? So what we have seen so far is that trans Z models translation of any relation in the same embedding space. So the question is, can you design a new space for each relation and do the translation in a relation-specific space? And the method that proposed this idea is called trans R, and it models entities as vectors in the entity space, so entities as points, and models each relation as a vector in the relation space together with a relation-specific transformation or projection matrix. So let me give you the idea how this works. So the idea is, as I said, trans R models entities as points, and for every relation we are actually going to learn two things. We are going to learn the translation relation vector, and we are going also to learn this projection matrix M for every relation. So the idea is, right, if I want to, the way I'm going to now predict relations, if I say are H and T related by relation R, I'm first going to apply matrix M to both points and basically transform them into a new space. And then in this new transformed space, I'm going to kind of apply the trans E intuition. So basically I'm going to use this vector to move around. So, right, I basically take the original embedding, I transform it according to the matrix M, which basically means I scale it, I rotate it, I translate it, and then I apply my vector R in there. So, you know, what will this buy me? For example, what this buys me is that it allows me to model symmetric relations. Because imagine, again, a symmetric relation like roommate, reciprocated, right? Then basically I can learn a roommate specific function, specific projection matrix M that will take two different points and map them into the same underlying point into the relation specific space. So it means that two people that are roommates will be able to be mapped into the same point, so that now here I'll be able basically to say no translation needed, R is 0, and I have this symmetric relationship right now. So this is what this allows us to do, which for example trans Z was not able to do. How about anti-symmetric relations? Again, we can easily do this, right? Because, for example, the translation matrix if I take two different points, the translation matrix can again transfer into this relation-specific space in such a way that the 2 points don't collide. And then the same way as in trans Z, we are able to do the same thing here, right? From head, according to the relation, I get to T, but from T, according to the relation, I don't get back to head. So this is also possible. So it can model both symmetric as well as anti-symmetric relations. Can this trans R also model one-to-n relations, right? Like student of. And actually, again, it turns out it can. Trans R can model this because, again, we have enough flexibility in the projection matrix R that can learn how to take, let's say, T1 and T2 and map them into the same point, so that when in this relation-specific space, I go from head according to the relation, I arrive exactly to T1 and T2 that are embedded to the same position. So in the original embedding, these are two different points, but in the, let's say, the relation-specific embedding that is achieved by this transformation matrix M, I can enforce T1 and T2 to be in the same point, so these one-to-n relations can naturally be captured. So this sounds great, right? It seems we have kind of fixed all the issues with trans Z. We can also do inverse relations, because the same way as we were able to do them in trans Z, we can do them in trans R, right? So basically we just, the transformation matrices for both relations have to be the same, and then, you know, one translation vector is the reciprocal or the inverse of the other translation vector. What is the issue? What is it not able to do that trans E was able to do is one thing, is composition relations, right? In trans R, you cannot do this type of composition of relations, right? Meaning, remember where you say, if x is related by y with R1 and y is related with z with R2, then x and z are related by R3. This was very easy to do in trans E because everything was in the same space and we just kind of moved around. But in trans R, we cannot do these composition relations. And the reason for this is that each relation has a different space. And we know how to model from the original space to the relation-specific space, but we don't know how to model between different relation-specific spaces. So these relation-specific spaces are not naturally compositional. So this means that composition relations trans R cannot do. So this was second method we discussed. So let's now talk about the third method as well, that is based on what is called bilinear modeling. And so far, right, we were using the scoring function simply as a distance in the embedding space. Like in trans E and trans R, we said the head plus relation should be close to the tail. But now, what if we change the embedding, the way we are scoring different relations? What if we change this function f, that it won't be a distance anymore, but something more interesting? So, for example, this mult is simply saying, let's embed entities and relations as vectors in the embedding space, kind of similar to trans Z, but let's use a different scoring function. Rather than using the distance as in trans Z, let's use this type of scoring function where we basically just have this bilinear model where we say the score is simply a coordinate-wise product of h, r, and t. Right? So the idea is if I have a h, r, and t, I simply multiply these things entry by entry, sum it up, and that is my score. And the idea is if head relation tail is true, then this score should be high, and otherwise this score should be low. The way you can think of this scoring function is that you can think of it as a hyperplane in the embedding space. So basically the way you can think of it is you can think of it as a cosine similarity between h times r and t. And cosine similarity is simply a cosine of the angle between two vectors. And what this means is that if the two vectors are orthogonal, then the cosine similarity will be 0. And if two vectors are completely aligned, the cosine similarity will be 1. Another thing that is important is that because this now defines like a hyperplane in the embedding space, this dot product can either be positive or it could be negative. And whether it's positive or negative, this tells me whether the point lies on the left hand side or whether it lies on the right hand side of the hyperplane. And hyperplane is really defined as a vector that is orthogonal to this hyperplane, and this vector is simply h times r, right? So basically h times r defines a hyperplane that is orthogonal to it, and then the tails that are related to h according to relation r should fall on the same side of the hyperplane as this normal vector is, and tails that are not related to it should fall on the other side of the hyperplane. So that's the intuition and the idea how this mult works. So can it do one-to-n relations? Yes, it can. The reason for this is because we can think again of a hyperplane, and if I have one-to-n relations, then T1 and T2 should fall on the same side or should fall on the same distance on or from the hyperplane, and that's easy to achieve. In terms of symmetric relations, again, we can naturally model this because multiplication is commutative, right? So we can flip the order in which we multiply things and we'll get the same value. So because summation and multiplication are commutative, this is naturally true. However, the limitation are anti-symmetric relations, right? Like a hypernym, part of, where the idea here is that dist mult cannot model anti-symmetric relations. Again, because of the commutativity of summation and product, it means you get symmetry, but you don't get anti-symmetry, right? H times R times T will always be the same as T times R times H, and that's the issue. So dist mult cannot do that. And then the other thing dist mult cannot do is modeling inverse relations, right? If H and T are related with R2, then they should also be related in the different direction with R1, like advisor-advisee type relation. And the reason dist mult cannot model this is because of the fact that it does not model inverse relations, or the only way to model inverse relation would be that R2 and R1 are equal. But semantically this does not make sense, because then the embedding of the relation advisor is the same as the embedding of the relation advisee. So basically this would mean that if I'm your advisor, you are my advisee, but at the same time, if I say, are you my advisor as well? The answer would be yes. And am I your advisee? The answer would be yes as well. So it would be like two symmetric relations rather than an inverse relation. So this is where dist mult fails. And then the last place where dist mult fails is composition relations, right? And the problem is that dist mult defines hyperplane for each head relation pair, and the union of hyperplanes induced by this composition of relations cannot be expressed by a single hyperplane. So kind of, a union or an intersection of hyperplanes is not a hyperplane anymore. So that's why that's the intuition why composition relations are also not possible. So the last method I want to talk to you about is called complex. And the idea here, the reason why I want to do this, is that we don't necessarily have to embed points into the simple Euclidean, real space. We can also have complex vector embeddings. We can embed them in complex spaces, right? So complex embeds entities using in the complex vector space, right? Where every point now has has a imaginary part and a real part. And one concept from complex algebra that is important to keep in mind is this concept of complex conjugate, where basically say if U is a complex number with real part A and imaginary part B, then a complex conjugate of it is simply that it's not plus B times I, but is minus B times I. And this notion of complex conjugate will be important as we analyze this model. So the way you can now think of this is that in complex we can actually use the scoring function that is simply similar to the scoring function in dist mult, but we are only then taking the real part of the complex function, because this would give me a complex number, so I want to only take the real part of it. So let's quickly analyze this approach as well. So can it model antisymmetric relations? Yes, it can. The way we can do this is that basically we can achieve that for different relations we get basically high or low value of our scoring function, basically due to the asymmetric modeling of complex conjugates, because here we are using the complex conjugate. Can we model symmetric relations? Again, yes, we can, because we can simply set the imaginary part of the relation to be 0, and then because everything works in the real part, we are able to model symmetric relations as well. And then, can complex model inverse relations as well? Yes, it can. How? By setting R2 to be a complex conjugate of R1, and this basically means that the real part of the two will be exactly the same, because what differs is only the complex part. So that is in terms of modeling inverse relations. How about composition and one-to-n relations? Because complex shares this property with dist-mult, meaning it uses the same scoring function, then it turns out that complex also cannot model composition relations as well as one-to-n relations, because it uses kind of a very similar scoring function. So this basically now concludes our discussion of different knowledge graph embedding methods for knowledge graph completion. We went through 4 of them. We went through TransZ, TransR, dist-mult, and complex. And what is interesting is that each of these methods has a bit different idea, right? The first two methods embed into the real space, so into the Euclidean space, but one uses the translation idea for every relation, while TransR also uses this transformation matrix M. And here I show different properties or different relation types that these methods can model. TransE is the only one that can model composite relations where they can be composed. dist-mult changes the scoring function. And complex actually embeds not into the Euclidean space but in the complex space. And the reason why I wanted to show you these different methods is to see kind of the diversity of options that embeddings allow you to work with, and give you a lot of freedom how you define your predictive model. So how do you do now knowledge graph embeddings in practice? Different knowledge graphs may have drastically different relational patterns and different properties. So it is not that there is one method that works best on all of them. It really depends on what kind of relationship types you are interested in modeling and what kind of relations do you want to predict. If you really want to predict one-to-n relations and model one-to-n relations, then don't use TransZ. If you really care about composite relations and this kind of compositions, then use, for example, TransZ. If what you care about, for example, would be anti-symmetric relations, don't use dist-mult, and so on. So it really depends on the graph and what you want to do. In general, TransR and complex have the most are able to model the most diverse set of different relation types. So what you can always try is try with TransZ, because it's very simple and has a very nice intuition. And then you can use more expressive model like complex, TransZ. There is also a model called rotate-E, which is TransZ but with complex embeddings. So there is a lot of different approaches and different ideas here. There's a paper linked up here that serves as a very good follow-up reading if you are interested in this topic. So to summarize, we talked about the knowledge graph embedding and knowledge graph completion task as one of the very important tasks in knowledge graphs. And we talked about 4 different methods: TransZ, TransR, dist-mult, and complex. Models with different embedding space and with different level of expressivity, allowing us to model different types of relationships.